Hello everyone, welcome back to my channel. In this video, I would like to explain what is linear programming and its applications and model formulations. As we know that linear programming is a widely used mathematical modeling technique developed to help the decision makers in helping in planning and decision making regarding optimal use of resources. In this video, I would like to explain the applications of linear programming in different functional areas of management and how LP models are formulated. Before getting into the topic, please subscribe to my channel. In this video, I would like to cover the following topics, that is introduction to linear programming and structure of linear programming model, advantages of linear programming, limitations of linear programming, applications of linear programming, general mathematical model of linear programming problem, guidelines on linear programming and model formulation, the application of specific operation research techniques to determine the choice among several courses of action so as to get an optimal value of the measures of effectiveness, that is objective or goal, requires to formulate a mathematical model. Such a model helps to represent the essence of a system that is required for the decision analysis. The term formulation refers to the process of converting the verbal description and numerical data into mathematical expression, which represents the relation among relevant decision variables and objectives and restrictions on the use of resources to several competing activities on the basis of given criterion of optimality. So before discussing the basic concepts and applications of linear programming, it is important to understand the meaning of the words linear and programming. The word linear refers to the linear relationship among variables in a model. That is, a given change in one variable causes a proportional change in another. Word programming refers to the mathematical modeling and solving of a problem that involves the use of limited resources by choosing a particular course of action among the given courses of action in order to achieve the desired objective. Now, coming to the structure of linear programming model. So, the general structure of the linear programming model. The general structure of an LP model consists of three basic components, that is, decision variables or activities, the evaluation of various courses of action, and select the best to arrive at the optimal value of objective function is guided by the nature of objective function and availability of resources. For this, certain activities which are called as decision variables, usually denoted by x1, x2, x3, x4 and so on up to xn are conducted. The values of these variables represents the extent to which each of these is performed. For example, in product mix manufacturing problem, an LP model may be used to determine units of each of the product to be manufactured by using limited resources such as persons, machinery, money, material, and etc. The value of a certain variable may or may not be under the decision maker's control. If values are under the control of the decision maker, then such variables are called to be controllable. Otherwise, they are said to be uncontrollable. These decision variables usually interrelated in terms of consumption of resources and requires simultaneously solutions. In an LP model, all decision variables are continuous, controllable, and non-negative. That is, x1 greater than or equals to 0, x2 greater than or equals to 0, and so on. xn greater than or equals to 0. Next, objective function. The objective function of each LP problem is expressed in terms of decision variables to optimize the criterion of optimality, and even it can be called as measure of performance, such as profit, cost, such as profit, cost, and revenue, distance, etc. In general, it is represented as minimum or maximize. Z equals to C1 x1 plus C2 x2 plus and so on up to Cn xn, where Z measures of performance variables, which is a function of x1 to xn, and quantities of C1 to Cn are the parameters that represents the contribution of a unit of respective variables x1 to xn to the measure of performance of Z. The optimal value of the given objective function is obtained by the graphical method or simplex method. Third one, constraints. There are always certain limitations or constraints on the use of resources such as labor, mission, raw material, space, money, etc. that limit the degree to which an objective can be achieved. Such constraints must be expressed as linear equalities or inequalities in terms of decision variable. The solution of LP model must satisfy these constraints. Next, assumptions of an LP model. In all mathematical models, assumptions are made for reducing the complex real-world problems into a simplified form that can be more readily analyzed. So, the following are the major assumptions of the LP model. First one, certainty. In LP model, it is assumed that all its parameters such as availability of resources, profit or cost, contribution per unit of decision variable, and consumptions of resources per unit of a decision variable must be known and constant. Second, additivity. The value of the objective function and the total amount of each resources used must be equal to the sum of respective individual contribution, that is profit or cost of the decision variables. For example, the total profit earned from the sale of two products A and B must be equal to the sum of the profits earned separately from A and B. Similarly, the amount of resource consumed for producing A and B must be equal to the sum of resources used for A and B individually. Next, linearity or proportionality. The amount of which resource used and its contribution to the profit in objective function must be proportional to the value of each decision variable. For example, if production of 1 unit of product uses 5 hours of a particular resource, then making 3 units of that product uses 3 into 5, that is 15 hours of the resource. Divisibility or continuity. The solution values of decision variables are allowed to assume continuous values. For instance, it is possible to collect 6.254 1000 liters of milk by a milk dairy. Such variables are divisible, but it is not desirable to produce 2.5 missions, and such variables are not divisible and therefore must be assigned integer value. Hence, if any of the variable can be assumed only integer values or limited to discrete numbers of values, LP models is no longer applicable. Advantages of using linear programming. Following are certain advantages of using linear programming technique. Linear programming technique helps decision makers to use their productive resources effectively. That is, to utilize the resources, available resources effectively. Linear programming technique improves the quality of decisions. The decision making approach of the user of this technique becomes more objective and less subjective. Linear programming technique helps to arrive at optimal solution of a decision problem by taking into account constraints on the use of resources. For example, saying that so many units of any product may be produced does not mean that all units can be sold. Linear programming approach for solving decision problem highlights bottlenecks in the production process. For example, when a bottleneck occurs, machine cannot produce sufficient number of units of a product to meet demand. Also, machines may remain ideal. Next, limitations of linear programming. In spite of having many advantages and wide areas of applications, there are some limitations associated with this technique. In spite of having many advantages and wide areas of applications, there are some limitations associated with this technique. They are as follows. Linear programming assumes linear relationship among decision variables. However, in real life problems, decision variables neither in the objective function nor in the constraints are linearly related. While solving an LP model, there is no guarantee that decision variables will get integer value. For example, how many men missions would be required to perform a particular job. A non-integer valued solution will be meaningless. Rounding off the solution to the nearest integer will not yield an optimal solution. The linear programming model does not take into consideration the effect of time and uncertainty. Parameters in a model are assumed to be constant, but in real life situations, they are frequently neither known nor constant. Linear programming deals with only single objective, whereas in real life situations, a decision problem may be conflicting and multiple objectives. Application areas of linear programming. Linear programming is the most widely used technique of decision making in business and industry and in various other fields. The broad application areas of linear programming are as follows. Applications in agriculture. These applications fall into categories of farm economics and farm management. The former deals with inter-regional competition, optimum allocation of crop production, efficient production patterns under regional land resources and national demand constraints, while the latter is concerned with the problems of the individual farm, such as allocation of limited resources such as acres, labor, water supply, working capital, etc., so as to maximize its net revenue. Applications in military. Military applications includes first one is selection of an air weapon system against the enemy. Second, ensuring minimum use of aviation gas line. Third, updating supply chain to maximize the total tonnage of bombs dropped on a set of targets and takes care of the problem of community defense against disaster at the lowest possible cost. Next, production management. First one is product mix. To determine the quantity of several different products to be producing, knowing their per unit profit contribution and amount of limited production resources used. The objective is to maximize the total profit subjected to the all constraints. Next one is product planning. This deals with the determination of minimum cost production plan over the planning period of an item with the fluctuating demand while considering the initial number of units in inventory, production capacity, constraints on production, manpower, and all relevant cost factors. The objective is to be minimize the total operation costs. Assembly line balancing. This problem is likely to rise when an item can be made by assembling different components. The process of assembling requires some specified sequences. The objective is to minimize the total elapsed time. Next one is blending problems. These problems arise when the product can be made from a variety of available raw materials, each of which has a particular composition and price. The objective here is to determine the minimum cost blend subjected to availability of the raw materials and minimum and maximum constraints on certain product constituents. Trim loss. When an item is made to a standard size, for example, glass, paper sheet, etc., the problem of determining which combination of requirements should be produced from standard materials in order to minimize the trim loss arises. Next, financial management. First one is portfolio selection. This deals with the selection of specific investment activity among all several other activities. The objective here is to find the allocation which maximizes the total expected return or minimizes the risk under certain limitations. Next is profit planning. This deals with the maximization of the profit margin from investment in plant facilities and equipment, cash in hand, and inventory. Next, marketing management. First one is media selection. The linear programming technique helps in determining the advertising media mix so as to maximize the effective exposure, subjected to limitation of budget, specified exposure rates to different market segments, specified minimum and maximum number of advertisements in selection of media. Next, traveling salesman problem. The salesman problem is to find the shortest route from a given city to each of the specified cities and then returning to the original point of departure, provided no city would be visited twice during the tour. Such type of problems can be solved with the help of the modified assignment technique. Physical distribution. Linear programming determines the most economic and efficient manner of locating manufacturing plants and distribution centers for physical distribution. Next one is personal management. Under personal management, staffing problem. Linear programming is used to allocate optimum manpower to a particular job so as to minimize the total overtime cost and total manpower. Determination of equitable salaries. Linear programming technique has been used in determining equitable salaries and sales incentives. Next, job evaluation and selection. Selection of suitable person for a specified job and evaluation of job in organizations has been done with the help of linear programming technique. Other applications of linear programming lies in the area of administration, education, fleet utilization, award contracts, hospital administration, capital budgeting, and etc. Now let us see general mathematical model of linear programming problem. The general linear programming problem with n decision variables and m constraints can be stated in the following form. That is optimization of maximization or minimization. Z equals to C1 into X1 plus C2 into X2 and so on up to Cn Xn, where Z is the measure of performance variables which is function of X1, X2, Xn, and C1, C2 are the parameters that represents the contribution of unit of the respective variables X1, X2 and so on up to Xn to the measure of performance of Z and subjected to the linear constraints up to m constraints, and here it may be less than or equals to and greater than or equals to, and non-negative constraints. It is mean that the production or the decision variables always it will be greater than or equals to 0, and the formulation can be expressed in a compact form as follows. Objective function z equals to summation of z equals to 1 to n and cj into xj subjected to the constraints. Now the constraints are made to compact, that is summation of j equals to 1 to n aij xj, and it may be inequality or equality, that is equals to bi, and where I equals to 1 to m are the constraints, and non-negative constraints are xj greater than or equals to 0, where j equals to 1 to n. So this is non-negative condition, where cj's are coefficient representing the per unit profit or cost of decision variables xj to the value of objective function. The AIJs are referred to the technological coefficients, and these represents the amount of resources, say I consumed per unit of variable xj. These coefficients can be positive, negative, or 0. The BI represents the total availability of the ith resource. The term resource is used in a very general sense to include any numerical value associated with the right hand side of the constraint. It is assumed that BI greater than or equals to 0 for all i's. However, if any BI less than 0, then both sides of the constraint I is multiplied by -1 to make bi greater than 0 and reverse the inequality of the constraint. In general, LP problem has the expression less than or equals to, greater than or equals to. Means that in any specific problem, each constraint may take only one of the three possible forms. That is less than or equals to, or greater than or equals to. Guidelines on linear programming model formulation. The effective use and application requires as a first step the mathematical formulation of an LP model. Steps of LP model formulations are summarized as follows. First one is identify the decision variables, and this can be divided into three steps. That is, first A, express each constraint in words. For this, you should first see whether the constraint is of the form greater than or equals to, that is at least as large as, of the form, or less than or equals to, no larger than, or it is exactly equals to. And now in the step B, express the above in the verbally the objective function. Next, step C, verbally identify the decision variables with the above two steps. For this, we need to ask a question, that is, what decisions must be made in order to optimize the objective function. Having followed three steps, decide the symbolic notations for the decision variables and specify their units of measurements. Such specification of units of measurement would help in interpreting the final solution of the LP problem. Next, identify the problem data. To formulate an LP model, identify the problem data in terms of constants and parameters associated with the decision variables. It may be noted that the decision maker can control values of the variables but cannot control the values in data set. Step 3. Formulate the constraints. Convert the verbal expression of the constraints in terms of resource requirement and availability of each resource. Then express each of them as a linear equality or inequality in terms of the decision variables which have been defined in step 1. Next, step 4. Formulate the objective function. Identify whether the objective function is to be maximized or minimized. Then express it in the form of linear mathematical expression in terms of decision variables along with profit contributions associated with them. After gaining enough experience in model building, we may skip verbal description. Let us see some of the certain examples of LP model formation that may be used to strengthen the ability to translate a real life problem into mathematical problem. A manufacturer produces two types of models, M1 and M2. Each model of the type M1 requires 4 hours of grinding and 2 hours of polishing, whereas each model of the type M2 requires 2 hours of grinding and 5 hours of polishing. The manufacturer have 2 grinders and 3 polishers. Each grinder works 40 hours a week and each polisher works for 60 hours a week. Profit on M1 model is 3 rupees and model M2 is 4 rupees. Whatever produced in a week is sold in the market. How should the manufacturer allocate production capacity to the two types of models so that he may make maximum profit in week? Let us see the solution. Here the manufacturer produces the two types of models, that is M1 and M2, and each of the model of the type M1 requires 4 hours of grinding and 2 hours of polishing. And whereas each model of type M2 requires 2 hours of grinding and 5 hours of polishing. And the manufacturer is having 2 grinders and 3 polishers. And for this, the work per week is 40 hours for the grinder and 60 hours for the polisher. So next is profit on M1 is 3 rupees and profit on M2 is 4 rupees. And whatever he has produced in a week will be sold in the market. So how should the manufacturer should allocate the production capacity to the two types of models? Let us find. So let X1 and X2 be the number of units of M1 and M2. And next, the objective function can be written as, since the profit on M1 is 3 rupees and profit on M2 is 4 rupees. So the objective function maximize Z equals to 3x1 plus 4x2 subjected to constraints are grinding machine and polishing machine. So here the number of grinders are available is 2 and the hours of available in grinding machine per week is 40 hours. So therefore the total number of available grinders is 80 hours, that is 2 into 40. So the constraint can be written as 4x1 plus 2x2, where 4 is the required for M1 and 2 is the required for M2. Next, number of polishers are 3 and the hours available in polishing machine is 60 hours per week. So the total number of availables of polishers is 3 into 60. So which will be 180 hours. So the constraint can be written as 2x1 plus 5x2 less than or equals to 180. Here less than or equals to indicates that it cannot be more than available hours. And next one is non-negative conditions. So the non-negative restrictions are x1, x2 greater than or equals to 0 if the company is not manufacturing any products. Problem number 2. A factory manufactures two products A and B. To manufacture one unit of A, 1.5 mission hours and 2.5 labor hours are required. To manufacture product B, 2.5 mission hours and 1.5 labor hours are required. In a month, 300 mission hours and 240 labor hours are available. Profit per unit for A is 50 rupees and for B is 40 rupees. Formulate as LPP. So it is clear that A and B are the two products. Let us assume as X1 and X2. So here to manufacture A, 1.5 hours of mission is required and 2.5 labors is required. Similarly, to manufacture the product B, 2.5 hours of mission and 1.5 hours of labor is required. So for a month, the available hours for the mission is 300 and for the labor is 240. And the profit for unit A is 50 rupees and for B is 40 rupees. So now let us formulate as a table, that is product A and B, and mission hours for product A is 1.5 and mission hours for product B is 2.5 and total availability of hours is 300. Similarly, labor for A is 2.5 and for B is 1.5, and total available labor hours per month are 240. Now, as the decision variables are x1 equals to number of units of A manufactured per month, x2 is equals to number of units of B manufactured per month. So the objective function is maximize z equals to 50x1 plus 40x2. Next constraints. First constraint is mission. So here 1.5 x1 plus 2.5 x2, and the availability hours is 300, so it is less than or equals to 300. So the constraint for mission hours. Similarly for the labor, that is 2.5 x1 plus 1.5 x2 less than or equals to 240. So this is for labor hours. And non-negative constraints is x1, x2 greater than or equals to 0. If even the manufacturer does not produce, it will be equals to 0 only. ABC Food Company is developing a low-calorie, high-protein diet supplement called HiPro. The specifications of HiPro have been established by a panel of medical experts. The specifications, along with the calorie, protein, and vitamin content of three basic foods, are given in the following table. So, for calories, in the food 1, 350, and food 2, 250, and food 3, 200, and basic food HiPro specification is 300. So similarly for proteins, vitamin A, vitamin C, and cost per serving each food is 1.50, 2 rupees, and 1.20 for the foods 1, 2, 3 respectively. And what quantities of food 1, food 2, food 3 should be used. Formulate this problem as a linear programming model to minimize the cost of serving. So the solution is, so the given table has been taken like as it is. So the decision variables are here 1.50 and 2 and 1.20, which has to be minimized. So let x1, x2, x3 are the quantity of foods 1, 2, 3 to be used respectively. So the objective function is minimize 1.5 x1 plus 2 x2 plus 1.2 x3 subjected to constraint. So the first constraint is calories. So 350 x1 plus 250 x2 plus 200 x3 should be greater than 300, and it is for calories. Next for proteins, 250 x1 plus 300 x2 plus 150 x3 greater than or equals to 200. It is for proteins. And next similarly for vitamin A, 100 x1 plus 150 x2 plus 75 x3 greater than or equals to 100. It is for vitamin A. Similarly 75 x1 plus 125 x2 plus 150 x3 greater than or equals to 100. It is for vitamin C. And finally, the non-negative constraints are x1 greater than or equals to 0, x2 greater than or equals to 0, x3 greater than or equals to 0. Another problem. A manufacturing company is engaged in producing three types of products A, B, and C. The production department produces each day components sufficient to make 50 units of A and 25 units of B and 30 units of C. the management is confronted with the problem of optimizing the daily production of the products in the assembly department, where only 100 man hours are available daily for assembling the products. The following additional information is available. That is, three products and profit contribution for each product is 12, 20, 45, and assembly time for each product is 0.8, 1.7, 2.5 respectively. The company has a daily order commitment for 20 units of product A and total 15 units of product B and C. Formulate this problem as an LP model so as to maximize the total profit. So it is clear that a manufacturing company has three products by name each A, B and C, and the production department produces each day, which is 50 units of A and 25 units of B and 30 units of C. And here the assembly department has only 100 man hours for assembling the products, and the company has committed for 20 units of product A and a total of 15 units of product B and C. So now let us formulate the LP model so as to maximize the total profit. So here I have taken this, or I have summarized the given data into an tabular column. So that is, the products are A, B and C. So next, the production capacity of A is 50 and B is 25 and C is 30. And man hours per unit is 0.8, 1.7, 2.5. It is the verbal content has been transformed into an tabular column. And as we know that the order commitment is 20, 15 and both for B and C. And the profit for A is 12 and profit for B is 20 and profit for C is 45. And the total hours is 100. Now let x1, x2 and x3 equals to number of units of product A, B and C to be produced respectively. So the first constraint is, the objective function can be written as maximize total profit Z equals to, that is, product of A cost profit, product A profit into quantity, that is x1, plus product B profit into quantity x2, and product C profit and count x3. So the total profit, that is maximize Z equals to 12x1 plus 20x2 plus 45x3. And coming to the constraints. So here the constraints are labor and materials is 0.8 x1 plus 1.7 x2 plus 25 2.5 x3 less than or equals to 100. And next one is x1 is less than 50, x2 less than 25, x3 less than 30. And the order commitment is product A is 20 and product B and C is 15. So this is the objective function and these are the constraints, two constraints. One is regarding labor and material and another one is order commitment. And finally, non-negative constraint is x1, x2, x3 greater than or equals to 0. Let us see one more example regarding the advertising. An advertising company wishes to plan an advertising campaign for three different media: television, radio, and a magazine. The purpose of advertising is to reach many potential customers as possible. The following results of a market study. So here are the resources are: cost of an advertising unit, number of potential customers, to reach per unit, number of women customers reached per unit. So A, that is 40,000, and number of potential customer reached per unit A is 4 lakh, 3 lakh, and rest of the data has been given for A, B, C, D. Now let us see the question. The company does not want to spend more than 8 lakhs on advertising. It is further required that at least 2 million exposures take place amongst women. The cost of the advertising on television be limited to 5 lakhs. At least 3 advertising units be bought on prime day and 2 units during prime time. And the number of advertising units on the radio and the magazine should each between 5 and 10. Formulate this problem as an LP model to maximize potential customer reach. Let us see the solution. Given that, let x1, x2, x3 and x4 equals to number of units bought in prime day, television, magazine and radio. Next, so the LP model is maximize z equals to 4 lakhs x1 plus 9 lakhs x2 plus 5 lakhs x3 plus 2 lakhs x4. Now subjected to the constraints, first one is budget, that is advertising budget is 40,000 x1 plus 75,000 x2 plus 30,000 x3 plus 15,000 x4 less than or equals to the budget is 8 lakhs as given in the problem. So next constraint, number of women customers to reach. So number of women customers to be reached by the advertising campaign is 3 lakhs x1 plus 4 lakhs x2 plus 2 lakhs x3 plus 1 lakh x4 greater than or equals to 20 lakhs. Next constraint on TV advertising. So that is 40,000 x1 plus 75,000 x2 less than or equals to 5 lakhs. And fourth constraint, this is for A and for B, x1 greater than or equals to 3, x2 greater than or equals to 2. And fourth constraint is on radio and magazines equals to 5 less than or equals to x3 less than or equals to 10, and B is 5 less than or equals to x4 less than or equals to 10. So the first constraint is on budget and second constraint is on women customers and fourth one is TV, and fifth one is radio and magazine. And finally, the non-negative constraints are x1, x2, x3 and x4 greater than or equals to 0.
Let us see another example. An electric company is engaged in the production of two components C1 and C2 that are used in radio sets. Each unit of C1 costs the company 5 rupees in wages and 5 rupees in material, while each of C2 costs the company 25 rupees in wages and 15 rupees in material. The company sells both products on one period credit terms, but the company's labor and material expenses must be paid in cash. The selling price of C1 is 30 rupees per unit and C2 is 70 rupees per unit. Because of the company's strong monopoly in these components, it is assumed that the company can sell at a prevailing prices as many units as it produces. The company's production capacity is, however, limited to two considerations. First, at the beginning of period 1, the company has an initial balance of 4000 rupees, that is cash plus bank credit plus collections from the post credit sales. Second, the company has in each period 2000 hours of mission time and 1400 hours of assembly time. The production of each C1 requires 3 hours of mission time and 2 hours of assembly time, whereas the production of each C2 requires 2 hours of the mission time and 3 hours of assembly time. Formulate the LP as an LP model so as to maximize the profit to the company. Let us know the data. So as we know that a company has production of two components, that is C1 and C2, while C1 costs 5 rupees in wages and 5 rupees in material, and C2 costs 25 rupees in wages and 15 rupees in material. And the selling price of C1 is 30 rupees and selling price of C2 is 70 rupees. And it has a total availability of cash is 4000 rupees. And the budget for the C1 and C2, 10 units per unit and 40 units per unit. And the mission time for the C1 is 3 hours per unit and 2 hours per assembly time. And whereas for the C2 it requires 2 hours of mission time and 3 hours of assembly time. Now let us formulate the problem as an LP model. Now I have summarized the given data into a tabular column, and here is the mission time, that is for A is 3 hours per unit and for B is 2 hours per unit, and availability of mission time hours is 2000 hours. And assembling for a unit A, that is C1, is 2 hours per unit and 3 hours per unit per B, and the available hours are 1400 hours. And the selling price of the A is 30 rupees and the selling price of B is 70 rupees. And the cost per A, that is manufacturing cost of A, is 10 and B is 40. So now let X1 and X2 be the number of units of components of C1 and C2. C1 and C2 to be produced respectively, as the function is maximize. So maximize Z equals to selling price minus cost price. So selling price here is 30 minus the cost is 10 into X1 plus selling price of second unit is 70 minus 40 is the cost price into X2, which can be written as 20 X1 plus 30 X2. Next, total budget available is 4,000 rupees. So the constraint according to budget is 10x1 plus 40x2 less than or equals to 4,000. So as the budget is only 4,000, it should be either less than or equals to. Next, production time. Production time equals to, first, mission hours, 3x1 plus 2x2 less than or equals to 2,000 hours. And next one is assembling time, 2x1 plus 3x2, and available time is 1400 hours. So the objective function is 20x1 plus 3x2, and the constraints are three constraints. One is budget constraint, and second one is machine time, and third one is assembly time. And finally, last but not the least, is non-negative constraint. It is x1 and x2 greater than or equals to 0. Let us see another example. A tape recorder company manufactures models A, B and C, which have profit contribution per unit of rupees 15, 40 and 60 respectively. The weekly minimum production requirements are 25 units per model A, 130 units for model B and 55 units for model C. Each type of recorder requires a certain amount of time for manufacturing of component parts, for assembling and for packing. Especially a dozen units of model A require 4 hours of manufacturing and 3 hours of assembling and 1 hour for packing. The corresponding figures for dozen units of model B are 2.5, 4 and 2, and for a dozen units of model C are 6, 9 and 4. During the forthcoming week, the company has available 130 hours of manufacturing and 170 hours of assembling and 52 hours of packing time. Formulate this as an LP model so as to maximize the total profit to the company. Let us see the solution. So here the production requirements are, per A is 25 and per B is 130 and per C is 50. And the manufacturing time, assembling time, packing time of A and B, C are given, and the total available hours are given, and contribution per unit A, unit B and unit C. Now, so as to maximize, first let us take x1 equals to A, x2 equals to B and x3 equals to C. As the function is maximization, maximize z equals to 15x1 plus 40x2 plus 60x3. So this is the objective function. Now let us find the constraints. So the first constraint is according to manufacturing time. So here manufacturing time is the first constraint. So it is 4x1 plus 2.5 x2 plus 6x3 less than or equals to 130. And here they have given according to dozen. So divide each term with 12. So they have not given per unit, they have given per dozen. So divide every term with 12. So next one is assembly time. So assembly time equals to 3x1 divided by 12 plus 4x2 divided by 12 plus 9x3 divided by 12 less than or equals to 190. Packing time. So x1 divided by 12 plus 2x2 divided by 12 plus 4x3 divided by 12 less than or equals to 52. So these are the three constraints. And coming to the finally the non-negative constraint is x1, x2, x3 greater than or equals to 0. In closing, I am grateful for your support and feedback. Remember to subscribe for more content and let's make a positive impact together. Knowledge is power. Let us change the world. Until next time, stay inspired and curious. If you have any questions, please email us at drawingforengineers@gmail.com and we'll respond with a video explanation. Thank you and see you in the next video.